China has built the most indestructible oil reserve in human history, carved directly into coastal bedrock, sealed by the laws of physics, and engineered to survive a war. We're talking about caverns operating completely maintenance-free for 50 years, at operating costs 50% lower than anything the rest of the world is running. That's not a typo. You heard that right. 50 years, not a single maintenance crew required, while every other nation on Earth is patching leaking steel tanks and losing oil to evaporation every single day. And while the world was distracted by tanker routes and pipeline politics, China was quietly solving an engineering problem that no other nation on Earth has cracked. The fatal flaw everyone shares. Picture the largest oil storage facility you've ever seen. Rows upon rows of massive steel tanks stretching to the horizon, gleaming in the sun, looking like the pinnacle of industrial engineering. Every major nation on Earth has built some version of this. The United States, Japan, South Korea, Germany, they all went above ground. They all chose steel, and they all inherited every single weakness that comes with it. Here's what that actually means in practice. Every one of those steel tanks is slowly dying. The moment you build a steel tank and fill it with crude oil, you've started a clock. The oil releases volatile compounds that evaporate straight through the tank walls, gone forever, unrecoverable, just wealth bleeding into the atmosphere. The steel corrodes from the inside out, from the outside in, from the top down. It needs constant inspections, constant recoating, constant repair, and the land those tanks sit on? Consumed permanently, tens of hectares per facility, land you can never use for anything else. But the evaporation and corrosion aren't even the most dangerous part. Every single one of those tanks is sitting on the surface of the Earth, fully visible from space, fully visible from the air, and fully destructible by anything with a guidance system. One missile strike on a surface tank farm doesn't just destroy oil, it triggers catastrophic fires that can burn for weeks, destroy neighboring tanks in chain reactions, and eliminate years of strategic reserves in a single afternoon. Military planners know this. Every adversary knows this. The vulnerability is so well understood that targeting surface oil infrastructure is literally a standard chapter in modern warfare doctrine. So every nation that went above ground didn't just choose an engineering solution, they chose an engineering liability. They built their energy security on a foundation that leaks, evaporates, corrodes, and can be erased from the map on a Tuesday afternoon. And Chinese engineers looked at every single one of those weaknesses, studied them in detail, and made a different decision entirely. But what they built underground is where this story gets truly extraordinary. The underground bet nobody made. While every other nation was perfecting the steel tank, Chinese engineers were asking a completely different question. Not, how do we build better tanks, but what if we didn't use tanks at all? In the early 2000s, China made a decision so audacious that energy analysts outside the country largely dismissed it. They were going to carve their strategic oil reserve directly into the Earth, into coastal bedrock, and let the planet itself become the container. No other major economy followed. Not the United States, not Russia, not the European Union. They all looked at the complexity, looked at the geology requirements, looked at the upfront engineering challenge, and they went back to their steel tanks. China didn't blink. And here's where the tension starts to build, because going underground isn't simply a matter of digging a hole and filling it with oil. The engineering challenge is almost incomprehensible. You need the right rock. You need the right groundwater conditions. You need geological formations that exist in very specific coastal locations, with very specific fracture patterns, very specific density profiles, and very specific depth characteristics. Get any single variable wrong and the entire system fails catastrophically, irreversibly, and expensively. This wasn't a gamble China could afford to lose. This was a national strategic decision, staked on the belief that their engineers could solve a problem nobody else had solved at this scale, in coastal terrain, under conditions that had never been tested before. But here's the payoff that makes your jaw drop. They didn't just solve it, they solved it so completely that the caverns they built in the early 2000s are still operating today without a single major structural intervention. The rock held. The physics worked. The engineering was right the first time. Every nation that dismissed China's underground strategy as overcomplicated, too expensive, or too risky, is now looking at 50-year maintenance-free infrastructure and trying to explain to their governments why they chose steel instead. But finding the right rock was only the beginning of the engineering challenge, and what came next pushed the limits of what humans can actually do underground. Finding the right rock. Before a single blast goes off, before a single tunnel boring machine rolls into position, Chinese geological engineers spend years doing something that looks less like construction and more like surgery. They are hunting for a very specific type of coastal bedrock, and the criteria are brutally unforgiving. The rock needs to be dense enough to bear the weight of hundreds of millions of barrels of oil pressing against it from the inside. It needs to have a fracture pattern tight enough that oil cannot migrate through microscopic cracks over decades. It needs to sit at exactly the right depth, deep enough to be protected from surface strikes, shallow enough to be economically excavable. And critically, it needs to sit below the natural groundwater table, because the entire sealing mechanism of the cavern depends on water pressure, doing a job that no mechanical system can replicate. You find the wrong formation, you build the wrong cavern, and you don't find out until it's too late. This is where the tension in China's engineering story becomes visceral. The Chinese coastline isn't uniformly blessed with ideal geology. Engineers had to survey thousands of kilometers of coastal terrain, drill test bores, run seismic analysis, model groundwater behavior across seasons and decades, and reject site after site that failed even a single criterion. The selection process is so demanding that viable locations are genuinely rare, which is exactly why no other nation attempted this at national scale. But when Chinese geologists found the right formations, and they found multiple, the payoff was staggering. Sites along the Shandong Peninsula, the Zhoushan Archipelago, and the Guangdong coast delivered bedrock conditions so ideal that engineers later described them as almost purpose-built by nature for exactly this application. Granite and gneiss formations with groundwater tables sitting at precisely the right elevation, fracture densities within acceptable tolerances, and load-bearing capacities that exceeded the engineering requirements by significant margins. Nature had already done half the work. Chinese engineers just had to figure out how to use it. But knowing where to build and actually building it are two entirely different levels of engineering nightmare. Carving chambers into earth. Now comes the part that makes civil engineers lose sleep. You have your site, you have your rock, you have your geological surveys, and now you have to hollow out chambers so massive that the numbers stop feeling real. Each cavern complex needs to store tens of millions of barrels of crude oil. To put that in physical terms, you are excavating underground spaces large enough to swallow multiple sports stadiums, stacked side by side, deep inside solid coastal bedrock. The excavation process starts with controlled blasting, but calling it blasting undersells the precision involved. These aren't demolition crews lobbing explosives into rock. These are teams of engineers calculating exactly how much charge, placed at exactly what depth, in exactly what pattern, releases the maximum amount of rock without fracturing the walls you intend to keep. A miscalculation doesn't just slow the project, it compromises the structural integrity of the entire chamber, potentially triggering collapses that would bury the investment and the workers simultaneously. And this is where the tension becomes almost unbearable. Because while the blasting teams are working from one direction, tunnel boring machines are advancing from another, carving the access tunnels and drainage channels that the entire operational system depends on. Coordinated wrong, and you have two teams of heavy machinery converging underground in fractured rock with nowhere to go. The logistical choreography happening hundreds of feet below the surface, in darkness, in rock dust, under millions of tons of earth. It is one of the most complex construction environments humans have ever attempted. But when the excavation is complete, the payoff silences every doubt. What emerges from the rock isn't a hole, it's a precision-engineered vault. Walls smoothed to specification, chambers dimensioned to exact tolerances, access tunnels positioned for optimal flow dynamics, drainage systems already channeling the groundwater that will soon become the cavern's permanent seal. The rock has been transformed from raw geology into engineered infrastructure, and it will stay that way, without significant intervention, for the next half-century. But the excavation is only half the engineering story, because what keeps the oil inside is where the true genius lives. Water seal. Physics as engineer. Here is the moment where China's underground oil storage stops being impressive and becomes genuinely genius. Because once those caverns are carved, Chinese engineers don't seal them with mechanical valves. They don't install pump systems to maintain pressure. They don't rely on any technology that can malfunction, corrode, or require replacement over a 50-year operational lifespan. Instead, they use something that has never failed once in the 4-billion-year history of this planet: the natural pressure of groundwater. The principle sounds almost too simple. The caverns are excavated below the natural groundwater table, which means the surrounding rock is saturated with water pressing inward from every direction. When you fill the cavern with oil, the oil floats on a layer of water at the base of the chamber. The groundwater pressure on the outside of the cavern walls is always slightly higher than the oil pressure on the inside. Physics does the rest. The water pushes in. The oil cannot push out. And the seal is maintained perpetually, automatically, without a single moving part. But here's where the tension sharpens, because this system only works if the groundwater table never drops below a critical threshold. If regional water levels fall due to drought, over-extraction, or geological shifts, the pressure differential collapses, and suddenly you have crude oil migrating through bedrock fractures toward the coast. Chinese engineers didn't just design for average conditions. They modeled worst-case groundwater scenarios across decades, built monitoring systems to track water table levels in real time, and in several facilities, engineered supplementary water injection systems that can artificially maintain hydraulic pressure if natural levels ever fall short. The payoff is a sealing mechanism that is simultaneously the simplest and most robust ever deployed in strategic energy infrastructure. No valve has a 50-year service life. No pump runs indefinitely without maintenance. But water pressure is governed by gravity? That has been running without interruption since the Earth formed. Every barrel of oil inside those caverns is being held in place by nothing more than the weight of water and the laws of physics. And the rock surrounding that oil is doing something equally extraordinary. Rock as container and vault. Steel tanks have one job: hold oil. They do that job adequately, and they fail at everything else. The rock surrounding China's underground caverns does 3 jobs simultaneously, and it does all 3 of them better than any man-made material on Earth. The first job is structural containment. The bedrock walls of these caverns are bearing loads that would buckle any engineered container. Hundreds of millions of barrels of crude oil pressing outward in every direction, continuously, for decades. Steel fatigues under that kind of sustained stress. It develops microfractures, work hardens, and eventually fails. Granite and gneiss don't fatigue. They don't develop metal fatigue cycles. The same rock that was bearing geological load for millions of years before the cavern was carved is still bearing load the day the cavern is decommissioned 50 years later. The container doesn't degrade because the container is a mountain. But this is where it gets even more extraordinary, and the tension builds the moment you understand what temperature does to stored crude oil. Surface steel tanks swing through brutal temperature cycles. Summer heat accelerates evaporation and degrades oil chemistry. Winter cold increases viscosity and complicates extraction. The oil in a surface tank is constantly being thermally stressed, constantly losing quality, constantly demanding climate management systems that consume energy and require maintenance. Underground, the rock maintains a near constant temperature, year-round, naturally, passively, permanently. No cooling systems, no heating systems, no energy consumed. The thermal mass of hundreds of thousands of tons of surrounding bedrock acts as the most effective insulation system ever deployed in energy infrastructure, and it costs absolutely nothing to operate. Then comes the revelation that reframes everything. Chinese engineers have explicitly designed these caverns to survive the overpressure wave generated by a nearby nuclear detonation. The rock absorbs and disperses blast energy in ways that no above-ground structure can replicate. You cannot destroy these reserves with a missile strike. You cannot destroy them with a bombing campaign. To eliminate China's strategic oil reserve, you would have to physically remove the coastal mountains of eastern China. And watching over every cubic foot of that rock, every second of every day, is something that didn't exist when the first caverns were built. Numbers that break your brain. At some point in an engineering story this extraordinary, you have to stop and let the numbers speak. Because the gap between what China built and what every other nation is operating isn't marginal. It's the kind of gap that makes you question every infrastructure decision the rest of the world has made for the last 50 years. Start with the operating lifespan. 50 years of maintenance-free operation. You heard that right. 50 years. The engineers who designed the first caverns will have retired, aged, and passed away before those caverns require a structural intervention. Every surface tank farm on Earth needs continuous maintenance from the day it opens. Inspection crews, recoating teams, valve replacements, pump overhauls, it never stops. It never gets cheaper, and it never gets less critical. Then look at the construction economics. China's underground caverns cost 20% less to build than equivalent above-ground surface tank capacity. That number alone should have triggered a global rethink of strategic reserve infrastructure. But the operating cost differential is where it becomes almost offensive. 50% lower operating costs, sustained across the entire 50-year lifespan. The compounding effect of that saving across China's total reserve capacity runs into figures that are difficult to process as real money. But this is where the tension sharpens into something visceral. Every nation running surface tank farms isn't just paying more. They're paying more while simultaneously losing oil they can never recover. Evaporation from surface tanks isn't a rounding error. It's a continuous, unrelenting bleed of stored energy into the atmosphere. China's underground caverns lose 0 barrels to evaporation. Not fewer barrels, 0. And then there's the land. 63 hectares saved per facility compared to equivalent above-ground storage. 63 hectares. That's roughly 156 acres of coastline that China kept, developed, or preserved for every single facility in the network. Multiplied across dozens of sites, that is a staggering amount of sovereign territory that was never surrendered to steel tanks. The numbers don't just make the case, they close it permanently. But numbers alone don't run a strategic reserve during a crisis. That requires something far more sophisticated watching over the entire network in real time. The digital twin watching everything. Every cavern in China's strategic reserve network is, in one sense, a sealed vault operating on the laws of physics. But in another sense, it is a living data environment, generating thousands of sensor readings every single minute. And sitting above all of it is one of the most sophisticated infrastructure monitoring systems ever built for an energy asset anywhere on Earth. Chinese engineers didn't just build caverns, they instrumented them. Sensors embedded in the rock walls measure stress at the microscopic level, detecting changes in load distribution that no human inspector could ever identify through visual examination. Pressure transducers track the hydraulic equilibrium between groundwater and oil continuously, flagging any deviation from the precise balance that keeps the water seal intact. Temperature probes map thermal gradients through hundreds of feet of surrounding bedrock. Oil level monitors track inventory in real time across every chamber in every facility simultaneously. And here's where the tension escalates. Because the volume of data coming out of a fully instrumented cavern network isn't something a human team can process. The sensor network generates more data in a single hour than an analyst could review in a month. A traditional monitoring approach would miss the signals buried in that noise. Microscopic changes in rock stress that precede a structural shift. Subtle groundwater pressure drops that indicate seasonal table movement. Early-stage anomalies that, left unaddressed, compound into genuine failures. China's answer was a fully integrated AI-driven digital twin, a real-time virtual replica of every cavern, every tunnel, every sensor node, and every pipeline connection in the network. The digital twin doesn't just display data. It interprets it, models it against decades of baseline readings, identifies pattern deviations that fall outside acceptable parameters, and alerts operators before those deviations become problems. The control room managing this system looks nothing like an oil depot. It looks like a space mission wall-size displays, real-time geological modeling, AI flagging anomalies across hundreds of simultaneous data streams while human operators make the decisions that matter. The rock holds the oil. The physics seals it. The AI makes sure nothing in that equation ever quietly goes wrong. But monitoring the reserve is only half of what makes this system a strategic weapon. Because getting the oil out, fast, to exactly where it needs to go, is where China's engineering masterstroke fully reveals itself. The network that moves it. Storing 300 days of oil underground is an extraordinary engineering achievement. but a strategic reserve that can't deliver its oil to refineries at scale, at speed, during the worst possible crisis conditions, is just an expensive hole in the ground. China understood this from the beginning, and the pipeline network connecting every cavern to the national refinery system is where the entire strategy snaps into focus. Every underground facility in China's reserve network is directly connected to the national pipeline grid, not loosely connected, not connected through intermediary transfer stations that add time and failure points. Directly connected, with dedicated high-capacity trunk lines running from the cavern access tunnels to refinery intake systems across the country. When China needs to move oil, it moves at industrial volumes through hardened underground infrastructure without a single surface transfer point that can be targeted or disrupted. But here's where the tension builds into something genuinely unsettling for every energy strategist outside China. During a crisis, the question isn't just whether you have oil. It's whether you can get the right oil to the right refinery through the right route faster than the crisis degrades your options. Supply chains under pressure don't fail all at once. They fray at specific nodes, in specific sequences, and the systems that survive are the ones that can reroute around failure in real time. China's AI optimization layer does exactly that. In real time, it calculates which caverns to draw from based on oil grade, geographic proximity to refineries, current pipeline capacity, and projected demand across the national grid. It models multiple crisis scenarios simultaneously, pre-positions drawdown sequences before they're needed, and reroutes flow automatically when pipeline segments go offline. The system doesn't wait for human operators to identify a bottleneck. It resolves the bottleneck before the operator sees it. The payoff is a strategic reserve that functions less like a storage system and more like a precision logistics weapon, one that gets faster, smarter, and more resilient exactly when the pressure on it is highest. And that design philosophy, building for maximum performance under maximum stress, is what makes the final chapter of this story the one that changes everything. Built for war, not disruption. Every nation on Earth with a strategic oil reserve built it to answer the same question. What happens if our oil supply gets disrupted? A sanctions event, a tanker shortage, a pipeline outage. They were designed for inconvenience. They engineered for a supply shock that lasts weeks or months, after which normal trade resumes and the tanks get refilled. That is the design philosophy, baked into every above-ground steel tank farm on every coastline in the world. China asked a different question entirely. Not, what if our supply gets disrupted? But, what if the world we depend on for oil stops existing in its current form? What if the disruption isn't a market event, but a military one? What if the shipping lanes don't reopen in 3 months because there are no shipping lanes anymore? What if this isn't a crisis you manage, it's a war you have to win? And here's where the tension of this entire story converges into a single devastating point. The difference between designing for disruption and designing for war isn't philosophical, it's physical. It's expressed in the depth of the rock above your oil. It's expressed in a water seal that no missile can breach. It's expressed in pipeline infrastructure buried beneath terrain that cannot be struck from the air. It's expressed in caverns explicitly engineered to absorb the overpressure wave of a nuclear detonation and keep the oil inside. Then came April 2026. The Strait of Hormuz closed. Tankers froze in place. Oil markets went into free fall. Nations that built their reserves in steel tanks watched prices detonate while they rationed supply, scrambled for alternatives, and prayed their above-ground infrastructure wouldn't become a target. China's refineries kept running. China's lights stayed on. China's AI pulled oil from indestructible caverns through hardened pipelines at exactly the volumes the national grid required automatically, efficiently, without panic. Every other nation built a reserve for the world as they hoped it would remain. China built a reserve for the world as it actually became. And carved into coastal bedrock, sealed by groundwater, watched by artificial intelligence, and hardened against nuclear overpressure, that reserve is still running right now.